IP addressing is one of the most important topics in information technology and software development. It's one of the key pillars that information technology and software development, as we know, is built upon, that web applications are built upon. Even people who are not into IP addressing, who don't know anything about it at all, they use IPs in their daily lives, and not even once maybe during the day, but several times. Because they're using their clients, their machines. It can be a smartphone if it's connected to internet service provider, it can be a laptop, it can be anything. In order, for example, to watch my video on YouTube, they are being routed based on their IP to YouTube's web servers, and that's how YouTube sends them the streaming data using UDP packets, and voila, they are watching my video. IP addressing is a very wide topic. So we'll start with small but determined steps to break down this topic into smaller segments so that it's more understandable, and we will build our knowledge on the foundations of what it is, where it came from, finally where we are going with IP addressing. Don't forget to watch my video about OSI model interconnect, because we will be talking about what layer IP addressing is on at the moment. And if you want, you might watch my video about UDP and TCP packets, because I mentioned them in my previous example. Let's start. Well, today we will focus mostly on IPv version 4. That being said, there are two versions of IPs. In order to understand the second version of IP, let's first understand what's the basic IP that was the foundation of IP addressing, IPv4, how it looks like and what it is. Well, you might look at IP as a unique ID, right? It's a unique ID that is assigned to machines, to clients that interact in the network. It can also be a router on layer 3 of OSI model. Here you might ask me, especially if you're studying for your CompTIA A+, well, but there are IMEI codes, right? There is a MAC address that is assigned to a hardware, right? Why do we need another unique ID? Like, why can't we use MAC address? Because MAC address is long, there are many different variations of it, and etc, etc. Well, we can't, because MAC address is used on the lower levels of networking. It's used by more primitive, I would say, networking equipment, such as switches on layer 2. Switches might use MAC addresses, and that's how we have ARPs, right? The list of allowed MAC addresses. However, in order to do the routing on a more smarter basis, when I say smarter, it means that the traffic goes through our router. It can be our home router or router in our corporate center, and the traffic needs to choose the fastest way, the shortest way to the destination. For example, if we're accessing the application, servers of which are based in South Africa, our traffic takes many different hops in order to reach those servers in South Africa. That's how people come up with different solutions, such as caching, so that it's cached, the traffic is cached closer to our location, and we don't have to travel all the way to web servers each time. If the servers are loading slower, it can be that the servers are very far from you, so latency increases, right? And all of that is done with the help of IP addresses. The traffic is routed with IP addresses. That's why on layer 3 we have another unique identifier, which is IP. IPv4, which was the first version of IPs, the unique identifiers, is a 32-bit set of numbers. Why I'm saying set of numbers instead of showing one IP right away is because there are different ways of presenting an IP, and I will explain you later why. So we have a dotted decimal notation, and this is notation that you are used to. This is a human readable notation of IP address. We have decimals in the first place, then dot, decimals, dot, decimals, dot, decimals, right? This is the IP address that we are used to. Why it's 32-bit? Well, if you divide 32 by 4 decimal groups, you will get that each decimal is 8 bits. So we have 4 8-bit decimal groups in an IP address. Each group is called an octet. So when we're talking about last octet, we mean 13 in this specific IP address. It's 10.11.12.13. When we're talking about first octet, it means I'm talking about 10, second octet 11, and third octet 12. You might ask, okay, does it mean that we can have like 1 milliard .11, .12, .13? Does it mean that we can have that IP address? No, you cannot. You are limited in the number of IP addresses that can be basically in the number that can be presented in each octet. And that number is from 0 to 255. So the maximum number in each octet is 225. So I can have an IP address 10, 11, 12, 255. But I cannot have an IP address 10, 11, 12, 256. And this stands for each octet. I cannot have 256, 11, 12, 255. Each octet is limited to 255. Now, if you remember from your probability questions at school or your mathematical task, you might recall that this means that we have limited IP addresses. So IP addresses are not unlimited. It's not an unlimited pool. Why? Because if you see that if we have 255 addresses in the first octet, 255 in the second octet, 255 in the third octet, and 255 in the fourth octet. I believe if we add a 0, because it can be 0 too, we'll get 256 possibilities. 0 plus 255, right? 256 possibilities for each octet. Now, on your math lessons, you might have been required to multiply different variations in order to understand how many possibilities we have, how many IP addresses we can possibly have with the variations, with the limits that we have. And the number is 256 multiplied by 256 multiplied by 256 and multiplied by 256, because we have 256 possibilities, number possibilities for each octet. I was lazy. I don't know what this number results to. But if you calculate it, or if you use your calculator to do it, please don't forget to add it to the comments down below so that other people can see how many total IPv4 addresses we have. That was enough. For some time, it was perfectly fine and people would live with that. However, as number of countries using internet increased and moreover, number of users using internet increased, humanity realized that they needed more IPs. Imagine each household has several devices now that are connecting to their Wi-Fi. Or there are more households, simply. We can see houses built everywhere, new apartments built everywhere, and each person moving into those apartments or houses, they have their own router with internet service provider. Long story short, we need more IPs. Even if this number is magically big, the result of this equation, we still need more IPs. It's not enough. And that's how IP became IPv4, which means that the standard version and older version of IP. The newer version of IP denomination became IPv6. In the next video, we'll talk about IPv6 in more detail, but here's how we came up with IPv6, because no one wanted to go from IPv4 to IPv6 without obvious reason. IPv4 is being used in the networking, and was ingrained into networking so hardly and so deeply that no one would come up with another version of IPv, which is IPv6, unless it was absolutely necessary. And in this case, it was, because we didn't have enough IPs. So this is a dotted decimal notation, official name of this version of IP address. And you might also read it as human readable format, or the standard format, how you know it. But why do we need to look at another notation? You might always think that, oh my God, things are always complicated. We look at the human readable format and then we look at binary format. By now, probably you might have heard what binary format is. It's a collection of zeros and ones. And this is the format that our computer understands. Our computer translates everything into that format so that it's easier for computers to comprehend. And again, I hear your question. You're saying, why do you complicate everything, Jama? Why can't we just stop at dotted decimal notation? Why should we look at binary version of the IP address? Well, the reason for that is that binary address, IP address, is not only used for computers in this specific topic, right? Binary version of IP addresses is being looked at during subnetting. This is when we have a specific range of IPs allocated for us. Very, very specific, like 10, 254, 254, 0 to 10, 254, 254, 255. This is the 255 addresses that we have been allocated. And looking just on numbers is difficult to calculate the correct range that we have been allocated. That's fine if you don't understand it fully yet. As we progress through the topic and with the next videos, you will have a better and deeper understanding. But we do need to understand that there is a binary representation of IP addressing. For example, the binary representation of this IP address 10.11.12.13 is this, as you may see on the screen. It's 4 zeros 1010 dot 4 zeros 1011 dot 4 zeros 1100 dot 4 zeros 1101. We will not be covering how to convert decimal dotted IP into binary, but if you do a simple Google, there are plenty of simple explanations or articles that you can find in Google. If you want me to make a video on how to do a conversion, please leave your comments in the comment section down below and let me know. So looking at IP addresses in binary format helps us with granularity. Why? Because it helps us to understand on a very, very detailed level what range of IPs we have. Because sometimes you might not have a chance to always put it in a human readable format. Your range of IPs is 10, 11, 12, 13. No. Sometimes what they do is that 10, 11, 12, 0, 8. This is your range of IPs. And you're like, what does it even mean, /8? Well, /8 is the subnet that you have. And by calculating the range of IPs, you will basically see what range of IPs you have. That's why for granularity, we need to understand the binary format of IP addressing. You don't necessarily have to calculate it, but if you are to calculate the subnetting, then you might need to understand it. However, there are plenty of online services that can do it for you. Well, when I was saying that the IP addresses are limited, you might ask me, and after you calculated this, well, we already don't have enough addresses. Like, how come we're even using IPv4 even now? Well, it's because there are different classes of IP addresses. One of the biggest classifications of IP addresses is private IP and public IP. On this diagram, I will help you to sort of understand it better, what private IP is and what public IP is. Public IP is a facet. It's a facet of our house, and this is what is visible to the people from outside. For example, we have a router, and it's our internet service provider's router, and any traffic coming from the internet comes to our router. And the destination address of the traffic that is coming is our router's public IP. 12, 13, 15, 16, right? For example, if you're trying to access something, request something from Google's web servers, from YouTube's web servers, the destination, there will be source, right? Address, which is the address of web server, and there will be destination address, destination IP, which is the public IP address of our router. And then the router, based on the internal rules that it has and the record, it will deliver the traffic to the correct end user. For example, there is you and there is your sister, and both of you are on your phones and you're accessing Instagram. When the traffic from Instagram hits the router, based on the IP, private IP that requested it, it will go to the specific user who requested it. So if it was me, then it will go to my phone's IP address. If it's my sister, it will go to my sister's IP address. The catch is that our IP addresses are private IP addresses, meaning that outer world don't see it. We are behind the curtains. We have public IP addresses, and everything that comes to one letterbox, which is a public IP address. What does it mean? It means that our private IP addresses of me and my sister can be anything from the range of private IP addresses. When I say the range, it means that we have a specific range of IPs that are private IPs. They cannot be assigned to a web server, internet-facing web server. When I say internet-facing, it means that they are accepting and sending traffic on the internet, right? On the internet-facing traffic server, private IP cannot be attached, or we cannot have private IP with our phones. It's only our router's IP that is usually private IP, public IP. And then the port forwarding is happening. Private IPs. There is a range of private IPs, for example, from 10.0.0.0 to 10.255, 255, 255, right? So 10.0.0.1 or 10.1.1.1 or 10.1.2.1, all of these are private IP addresses. And they are usually called Class A IP addresses. You don't have to remember what class they are, because honestly, in my experience, no one refers to them by the class. But in order to have a clearer classification of IP addresses, it was sort of a rule that to classify them into separate classes. So private IP addresses from 10 to 10.0.0.0 to 10.225, 225, 225 is class A. And in total, that gives us a little over than 16 million IP addresses. Not only IP addresses, private IP addresses, right? Also, we have a class B, second range of private IP addresses. It is 107.216, 00 to 172.31, 255, 255. So we basically have from 16 to 31. Second octet can change, and the third and fourth octets can change from 0 to 255. This gives us a little bit over than 1 million IP addresses, private, again, IP addresses. And the class C, the third range of IP addresses that we have, private IP addresses, is 192, 168, 292, 268, 255, 255. This is the shortest range because what can change is these last two octets, right? Here we can have some flexibility. From 0 to 255, and again from 0 to 255. Here we have some flexibility on these last three octets. It's 16 to 31 in the second octet, and last two are quite flexible. And here we have the highest number of flexibility with last three octets, where second octet can change from 0 to 255. That's why we have 16 million IPs in class A, 1 million IPs in class B, and 65k IPs, private IPs, in class C. Can we reuse private IPs? Well, given that we have a very limited number of private IPs, 16 plus 1 plus 65k, approximately, it makes something up to 18 million, right? Even maybe 17 million and a half. But the population of the Earth is much bigger, and people who are using internet, there are much more people who do that. It means that routers can reuse private IP addresses because nobody sees them. So the private IP addresses are behind the router. Web server of Google cannot send traffic to private IP address of user C. It will not go through the router. Router only accepts traffic to its public IP address. So we are behind the facade of the house, and the house has one letterbox. Everything should come to that letterbox, to the public IP of the router, which is unique, right? It is unique. But we can reuse private IP addresses. So if the postman comes, postman cannot throw a letter to my window, to my private IP address. This will not be accepted because my window is closed. It can only come through the public IP address, through the postbox, letterbox that we have on our door. This is an important point to understand because it leads us to more flexibility with IPv4, because we can reuse ranges of private IP addresses between the computers in our household, in the corporation, between computers of users in the corporation. Well, still we have a scarcity of IPv4 addresses, of public IPv4 addresses, because they are unique. right? We still have a scarcity. There are a couple of IP addresses that are not necessarily allocated on the subnet, not necessarily touched. And these are IP addresses that you might have to know about if you want to do troubleshooting, or if you're preparing for your exams, let's say. One of the IP addresses is loopback IP address. If you Google loopback jokes or loopback rugs, you will see some funny photos on Google, because loopback address is basically pinging the Ethernet, the network adapter, of the same machine, of the machine itself. It seems like, hello, is there someone? Okay, there is, I can hear it. Okay, then I exist. Or I ping my heart. Oh, hello, is there a heart? Are you beating? Okay, that means I'm alive. I exist. Well, this is loopback address works in a similar fashion. If you, on your computer, you run a command in terminal, ping, and loopback address 127.0.0.1, and you receive pings back, it means that you have an Ethernet card, right? You have a network adapter, you have a network interface. It means that you might be able to access the internet, but please don't confuse it with internet access. It has nothing to do with internet access. It only checks if you're alive, if you're here, if you have Ethernet profile to possibly have access to the internet, but it doesn't check your internet access. It just checks, hello, am I alive? You see? And alive, not in a sense of whether the computer is on, no. It checks whether you have appropriate Ethernet settings, Ethernet profile. Because if you don't have it, then you need to start working on creating an Ethernet profile, Ethernet settings, before you can even try to access the internet. And this address is usually called loopback. So whenever you see loopback, it's this address. There is also another IP address called default, 0000. If some server or router or client has 0.0.0 IP address assigned to them, it means that no IP address has been assigned. There has been an error, and you either need to assign an IP address or do further troubleshooting. So 0000 is just John Doe. It means that no name has been given, and you have to do some troubleshooting or assign an address. And obviously on 000 you will not be accessible from the internet. You need to do troubleshooting, but this IP is called default IP address. Now there is one more IP that is usually reserved, right? Reserved by the router. So for example, if router's public IP is 12, 13, 15, 16, right? And the range of private IP addresses is 10, 10, 11, 12. Like we can have the range from 10, 10, 11, 11 to 0 to 10, 10, 11 to 155. It doesn't mean that we can have a user who has this IP address 10, 10, 11 to 155. Last IP address is usually taken for broadcasting, for multicasting, and I will explain to you why. I will explain to you how that happens. So realistically, the list of the available IP addresses that users can take is 254. 10, 10, 11 dot 254, the last address. Why do we need a broadcast or multicast? What does it mean? So here, for example, if router wants to send the message, internet packet, to all of these users, it usually uses broadcast IP address to broadcast its message, right? On the very basic level, it's when we are broadcasting to all users on the network. However, we can look at it on a more detailed level. Like, in order to look at it on a more detailed level, let's first understand what is unicast. There is multicast, broadcast, and unicast. Unicast is, remember, it's one. We have a client. When I say client, it's basically a user, an outside user who's trying to access the server, the internet. We have a client, and we have an IP network, right? Internet. And the client is trying to access a web server. It can be google.com, right? And this is one-to-one communication in a very simplified format. There is one public IP of the server and the client is accessing it, right? Unicast, one-to-one, one-to-one. Nothing special. Not that nothing special about it, but I would rather say nothing complicated about it. We have a broadcast. Broadcast is when the message is delivered from one to many, right? The client is accessing the IP network, and from IP network via the router, right, the message is sent to all of these clients. It broadcasts the message to everyone. It's as if we have a tool to sort of say something, say certain message in very, very loud way so that everyone hears. This is one to many broadcast. In a multicast environment, which is a more not that it's more complex. No, it's when we have a router. So the client sends the packets. The client is sending the packets through the internet to the router on router's public IP address, right? However, behind the router, in comparison to this diagram where we have 3 users, we have 2 switches with different user groups, right? Behind the router, we have switch A and switch B. And behind the switches, we have users A and B behind switch A and C and D behind switch B. What is the use case, for example? We have a corporate router. It could be Google. And the network is going to the corporate router. Then there are switches in the web server room that distribute this traffic based on the departments or based on the divisions. So for example, switch A is accounting department and switch B is billing department, right? And this is the messages that come to switch A, accounting department. And there are employees A and B in accounting department. And what happens to the traffic? It goes through the internet, it reaches the router, and then router forwards this message to user A and user B through switch A. If it's for the billing department, then the router forwards this traffic to switch B, and the traffic is forwarded to users C and D. What is the point of this? So you might ask, can't we be just all on one router? Why should we introduce additional switches? Well, first of all, it's easier to manage. It's easier to understand what's wrong. It gives you granularity, the detailed view, or in case if there is an issue. Also, there is more room for failover. So for example, if there is only one switch behind the router and that switch breaks down, then I don't know what you're gonna do. I mean, you have to have a failover scenario, or all employees depend on you, etc., etc. But if there are smaller switches that distribute traffic, then you can just fail over those 2 users to switch B if something happens. And of course, it's security rules. So maybe accounting team cannot access YouTube, cannot access, I don't know, Facebook or some obviously adult websites. And you can have a control rules set up for on a smaller node before accounting team. And what if marketing team should be able to access YouTube? It might be related to their work line, and then they might have different networking rules. So this is one of the few use cases for that. But in multicast, you are announcing to certain group of computers. So you're using multicast IP that you have reserved to announce something to users of switch A only, right? Or to users of switch B only. You choose specific group to announce it to. It can be some technical announcement, some packages that we don't even see as users. So for example, it might be like, your IP range has changed, and you announce it to everyone. As users, you're not gonna notice anything at all. But on a networking layer, multicast IP, the reserved multicast IP is very important for router to make announcements to either a group of IPs, group of switches that are group of IPs that are behind a certain switch, to everyone during broadcast. And of course, in unicast, it's not that important, but we still usually reserve the last IP of the range as a multicast address. I hope this lecture was clear. If you have any questions, please leave them in the comment section down below, and see you in my next video. Thank you for being with me today. Have a nice day. Bye.